Hello and welcome to my new video. Today I will be talking about polar distributions, and as an example I will show you how to model this little erythrocyte here in the background. In my previous videos I had talked about linear structures like worms or snail shells. Now we start with our first planar structure. When it comes to distributing things on a plane or in space as well, there are mainly two types of systems, Cartesian ones and polar ones. Cartesian distributions are using two axes, three axes in space, to distribute elements. These axes are not necessarily arranged by right angles, and elements are not necessarily distributed with equal distances along all axes, but in most cases, as here, they are. Polar distributions, on the other hand, are defined by only one axis, where elements are distributed along. In a second step, elements are rotated around an axis perpendicular to the first axis by varying angles. We will speak about Cartesian distributions in another video. Here let's focus on polar distributions. How can we generate them? It's not difficult. Elements first are distributed along the x or y axis and then rotated around the z axis. Here you are. I will do this in slow motion now. So let's start with an empty two-dimensional coordinate system, and let's first distribute elements with equal distances along the x-axis. This distance will refer to the radius of the circles we are about creating. I will only show the first two of them here. For rotation around the z-axis in the first circle, we have to use an angle we can divide 360 degrees by without remainder. I chose 30 degrees for this example. When we apply this angle, we will distribute our element in an equal way around the first circle. If we double the distance from origin and simply keep our angle of 30 degrees, we would also double the distance between two elements, the arc between them. To have the same distance between two elements in circle 1 and 2, we have to halve this angle. So in the second circle, we will rotate elements by multiples of 15 degrees using the double amount of elements when compared to circle 1. In general, for the nth circle, we have to divide the initial angle by n. Using this halved angle for 15 degrees for the second circle, we obtain evenly distributed elements along both circles. Now, how can we translate this into some kind of 3D script? Let's start with a simple loop distributing the elements around one circle. In each step of this loop, we have to increase the angle by 30 degrees, starting from 0 up to 360 degrees. Let's call it angle loop. We calculate the position for each element and put a little sphere on this position. As an input to this loop, we need the radius and the initial angle. The number of loops will be necessary as input for our second loop. The second loop will work on multiples of the initial radius, starting from circle 1 with the initial radius until reaching the last circle with the final radius. For each radius, we have to go through a complete run of the angle loop, defining all positions in the respective circle. Prior to the angle loop, we have to define the angle for the respective circle, and after finishing the angle loop, we have to reset the angle value to 0 in order to be ready to start a new angle loop for the next radius value. Up to now, our structure is still a bit boring because it is completely flat. We can change this pretty easily by defining two arbitrary positions, P1 and P2, which will be used to change the z coordinates of the planar elements. For creating somewhat distorted erythrocytes, I've increased z coordinates depending on the distance to the 2 points. Elements close to either P1 or P2 obtained a larger distance to their z coordinate. Elements further apart from both elements obtained only slight increases. I chose a linear relation between distance to the points and increase in z coordinate, but other relations are possible, of course. In our script outline, we have to add this calculation of z coordinates to the angle loop, since it has to be done for each element separately. One final thing we have to add to our script outline is an if statement. We want the rim of the erythrocyte being somewhat thicker than the rest, so we have to increase the radius of the spheres from the outer circle by a certain amount. This picture here summarizes the creation of erythrocytes from position calculated so far using metaballs. In the first graph, metaballs have a very small radius. In the second graph, their radius is increased, making them fuse, and in the third graph, we have increased the size of metaballs from the outer circle. So this is all I wanted to show you about polar distributions and erythrocytes. In the background, you see our erythrocyte multiplied, randomly rotated, and distributed by a 3D Cartesian distribution. I will talk about such distributions in the next video.